Hello and welcome everyone to Science Era. In this video, we are going to look at chapter number 4, section 4.3, which deal with stoichiometry reaction. Before we begin our unit, first we need to understand some of the concept related to a reaction of stoichiometry. So first one is mole. Mole is amount of substance that contain exactly the same number of elementary particle as there are in carbon atom in 12 gram of carbon 12. Mass is a measure of amount of matter in an object or a measure of amount of matter on the of the object consists of. Mass is measured in grams and mole is measured in mole. Unit is mol, mole. The symbol for mole is N and symbol for mass is small m. Molar mass is the mass in grams of 1 mole of a substance. It is measured in gram per mole and the symbol for molar mass is capital M. Next is the volume. Volume is measured in dm cubed. It is the space a gas occupies and the symbol for volume is capital V. Molar gas volume is V with m small. It is measured in dm cubed per mole. The volume of a gas occupies at STP standard temperature and pressure. Standard temperature has a value of 273 Kelvin or 0 degrees Celsius and standard pressure has a value of 1,013 times 10 to power 5 pascals. Whenever there is a reference to STP, it means that temperature is 273 Kelvin and pressure is 1,013 times 10 to power 5 pascals. Next is concentration. Concentration is measured in mole per dm cubed. The number of moles of a substance dissolved in a specific volume of water, also called molarity, is the concentration and it is measured in mole per dm cubed. Other formulas can be used to express concentration. The one we use is called molarity. The molarity of a solution is its concentration expressed in mole per dm cubed, as I said. So let's look at some of the stoichiometric calculations. Calculating mass of reactant required in the reaction. Question states how many mole of iodine are required to react with 0.429 moles of aluminum according to the following equation. The equation states that 2 aluminum reacts with 3 iodine molecules to produce 2 molecules of aluminum iodide. Referring to the balanced equation, the stoichiometric factor relating to the two substances of interest is 3:2 moles. So 3 iodine moles reacting with the 2 aluminum moles. So 3 mole of I2 iodine over 2 moles of aluminum. What are we going to do? We are given moles of aluminum and we need to find the moles of iodine. We are going to approach it using the stoichiometric factor. So if we times moles of aluminum with stoichiometric factors, we will find out the moles of iodine. So moles of aluminum given in the question is 0.429 moles of aluminum, and the stoichiometric factor is 3 moles of I2 over 2 moles of Al, which will give you the moles of iodine. We are calculating the mole of iodine as the question have asked us to do. So if we times 0.429 moles of aluminum by 3 moles of iodine over 2 moles of aluminum, the stoichiometric factor, we going to get 0.6, sorry, 0.644 moles of I2 iodine. So 0.644 mole of iodine is required to react with 0.429 mole of aluminum according to the given equation. Next is number of product molecules generated by reaction. So in this question we are going to calculate the product molecules number, right? So question is, how many carbon dioxide molecule are produced when 0.75 moles of propane is combusted according to the equation. So equation here is C3H8 plus 5 O2 molecules reacting to produce 3 carbon dioxide molecules and 4 H2O water molecules. The approach to this question is same as the example we did before, although the absolute number of molecule is requested. So we're going to use the Avogadro's number. So we know that the balance equation show carbon dioxide is produced from propane in 3:1. Here is 1. We don't generally write 1, but if there is no number, it means 1. 3:1 ratio. So 3 moles of CO2 will produce 1 mole of C3 and H8. Okay, so first we're going to times, using the stoichiometric factor, the number of propane molecules with the stoichiometric factor, which is 3:1 ratio given as per the balanced equation, and in the next step we're going to find the molecules of carbon dioxide by timing the moles of carbon dioxide by Avogadro's number. So first step, use stoichiometric factor to find moles of carbon dioxide, and then next use Avogadro's number to find the molecules of carbon dioxide as required by the question. We need to find the molecules of carbon dioxide. So what are we going to say? 0.75, which is moles of propane as given in the question, times the stoichiometric factor or the ratio 3:1, and then we're going to times it by the Avogadro's number, which is 6.022 times 10 to power 23 carbon dioxide molecules over the carbon dioxide molecule, right? 1, which will give you for 1.4 times 10 to power 24, sorry, it's 24 CO2 molecules. Right, so we're going to time 0.75 moles of propane times it by 3 moles of carbon dioxide over 1 mole of C3H8 propane as given in the question, stoichiometric factor, Then we times it by Avogadro's number, which is constant value 6.022 times 10 to power 23, which will give you 1.4 times 10 to power 24 carbon dioxide molecules. Relating masses of reactant and products. What mass of sodium hydroxide would be required to produce 16 gram of the antacid milk of magnesia, magnesium hydroxide by the following reaction? We must derive an appropriate stoichiometric factor from balanced chemical equation and use it to relate the amount of two substances of interest. So what we're going to do is, in first step, we're going to take the mass of magnesium hydroxide and times it with the molar mass to get the moles of magnesium hydroxide. Then we're going to times that moles of magnesium hydroxide with the stoichiometric factor, which is 2:1. 2 sodium hydroxide molecules is reacting with 1 magnesium hydroxide. 2 sodium hydroxide molecule is reacting to produce 1 magnesium hydroxide. So these are the two uh, factors of interest. Moles of magnesium hydroxide is then times with the stoichiometric factor to which will give you the moles of sodium hydroxide. After that, we're going to times sodium hydroxide, number of moles of sodium hydroxide with the molar mass to get the mass of NaOH required by the question. So we know that 16 gram of magnesium hydroxide is given. We're going to times it with the molar mass, which is 1 mole of magnesium hydroxide over the 58.3 grams of magnesium hydroxide. Then time with the stoichiometric factor given in the question, which is 2:1. Then we're going to times it with the moles of sodium hydroxide, which is 40 grams NaOH over the mole of NaOH, which will give you 22 grams of sodium hydroxide as given in the equation. So 16 times 1 over 58.3 times 2 over 1 times 40.0 gram over 1 equals 22 grams of sodium hydroxide. Relating masses of reactant. What mass of oxygen gas O2 from the air is consumed in combustion of 702 grams of octane C8H18, one of the principal component of gasoline? So they are asking you to calculate the mass of oxygen if octane is used 702 grams in combustion. So we're going to follow the same guideline as we did for the last two examples. We're going to times mass of octane with the molar mass to get the moles of octane. Then moles of octane will be times with the stoichiometric factor given in the equation, balanced equation. Then that stoichiometric factor we're going to times it with moles of oxygen, moles of octane times with the stoichiometric factor will give you moles of oxygen. That will be times with the molar mass again to give you the mass of oxygen. So first times mass of octane, which is given in the question, 702 grams of octane. This is 702 grams of octane times the molar mass. Molar mass is 114.23 grams times the stoichiometric factor, which is 25 over 2. So we're only looking at the reactants here. 25 oxygen molecules over the 2 octane molecules times the molar mass of oxygen, which is 32 grams again, which will give you 2.46 times 10 to power 3 grams of 10 to power minus 3 grams of oxygen. The figure provides the summary or general outline of the various computational steps associated with many reaction of stoichiometry calculation. So if you have, for example, given moles of A and you need to find out the volume of a solution A. So what you're going to do is times it with the moles of A times the molarity will give you the volume of solution A. If you times moles of A with stoichiometric factor, it will give you moles of B. If you want to move from moles of A to mass of A, you times it with molar mass. From mass of A, if you want to find volume of a pure substance A, you're going to times mass by the density to find the volume. And to find the number of particles of A, times the mole of A with Avogadro's number. Same goes with the moles of B. So these are the general steps in calculating the various reaction in stoichiometry calculations. This brings us to the end of stoichiometric calculation, section 4.3 of chapter number 4. Thank you for watching. If you like my video, don't forget to subscribe for more.